We have now reached the final section, the final block of today. We have 3 more presentations to go, and then we'll be ready for dinner. And next up, we're going to be taking a closer look at predictive maintenance. Our speaker for this graduated with a degree in computer engineering. He later started to work as an innovation engineer on industrial human-machine interfaces. Today, he is responsible for the product roadmap of user software, which includes robot programming, simulation, and IoT solutions. And his appetite for user experience and strategy has gradually led him to product management positions. So please welcome now on stage from Stäubli, Global Software Product Manager, Clément Fournier. Welcome, Clément. Hi.
Hi.
Great to have you here.
Yeah, it's great to be back here. So it's the second time we participate to the get-together for robotics. So it's nice to see familiar faces we met last year. And also this year we came with a lot of people from Stäubli. We have almost an entire row here at the back. So that shows you how we love this event and we believe in the growth of SRCI in the coming years. So the purpose of this presentation is to talk to you about predictive maintenance, and this resonates well with what has been discussed during the roundtable when the people talked about how AI was a really hype word at the moment, and the hype was slowly going down. We faced a similar phenomenon with predictive maintenance a couple of years ago. Everyone was talking about it. A lot of companies joined the field claiming that they could do predictive maintenance stuff. And today, October 2024, it's still hard to see any predictive maintenance use case. Your robot is not telling you when it's going to break. Your car is not telling you how it's going to break. And similar for your smartphone device and dishwasher. So the goal is to understand what challenges we faced from the past couple of years working on predictive maintenance at Stäubli, and where we stand at the moment. So first of all, who we are at Stäubli. So we're a Swiss company founded in 1892. So the big part of the R&D and production is located in Annecy in the French Alps. So this is why I have this French accent. We have 28 business units, so a worldwide presence, and 6,000 employees spread across 3 divisions. So the historical division was the textile division. So we built components for textile industry. And then we diversify with a connectors division. So this is also what we were very famous for, electrical and fluid connectors. And the latest division that was created was the robotics division, created in 1982, so which makes us a bit of the grandpas of robotics. But despite being grandpas, we've kept a lot of appetite for innovation over the years. And so I will not go over all the dates here, but one important one is 2001. This was the big first step of Stäubli inside of the digital realm with the Stäubli Robotics Suite, which is still up and running today to program and do simulation on the robots. And then gradually improving the robot range with new robots. And when you say new robots, robots have been equipped with more and more sensors into them. We now have a lot of temperature sensor, current sensors in both the robotic arms and the controller. So we are able to generate more and more data. So at some point we said, okay, what can we do with the data? Because the data being generated by the robot is of course really interesting for everyone revolving around a robotic project. So the integrator, looking to get the data to optimize the robot cycle time. The end user is, of course, interested in the data to put the production process under control and to be able to detect a deviation in the production process. And a third actor, which is really interested by the data, is, of course, Stäubli, because we take the data when a robot is failing to understand what's going on and to be able to build longer-lasting robots. So everyone is interested by the data. And because we have a large amount of data, this is where AI comes into play, because AI is good at processing and handling large amount of data. And in robotics, we have different categories of AI, and some categories we've talked about it in earlier presentation. So we have AI applied to application-based in robotics, so everything related to motion planning, being able to teach a robot to perform a task he hasn't done before. We have AI related to copilot use cases, to be able to ask ChatGPT-like questions, to write some code, to generate some code. So this is what we put in the copilot category. We have everything related to plant level, so not a robot-centric approach, but mostly at the plant level to optimize the production scheduling and the process optimization. And finally, we also have maintenance to be able to detect and do predictive maintenance. So this is a general landscape of AI in robotics. And now, so where do we stand? Predictive maintenance being the long-term vision, the end goal for us. We have segmented our predictive maintenance journey in 4 different steps. So the step 1 is to be able to detect that an issue is going on. So detect that a robot is not behaving the way it should be. So this, of course, allows us to detect something is going on before we get a downtime. Sorry. And then this is done based on human knowledge. So based on our 40+ years of experience in robotics, we have defined a sets of rules that we have implemented in an algorithm. So this is not related to AI, but traditional algorithms are also really good at detecting abnormal behavior. So this is step 1. Then we have step 2. Step 2 is to do the exact same thing, to be able to detect an issue based on AI. So to train a model to recognize a defect. Then step 3, now that we have detected the issue, it is time to classify, so to be able to know the root cause of the issue. So this is what we call the classification. And finally, this is where we reach the final stage, prediction. So prediction is to be able to detect, classify, and to know in advance when a specific subcomponent of the robot is going to fail. So now we will dive in more details into each one of those steps to understand every challenge we faced and the lessons we learned from it. Beginning with step 1. So step 1, this is the current stage, I would say. So this is what we have right now on the market. So we have a product which is called Scope, which is technically a big IPC with a big storage and a big computing power. That is installed on the production line and doing continuous analysis on the robot data. And this plays a role into 2 core pillars of the product life, the robot life, sorry. During the commissioning, because Scope will help find the right balance between cycle time optimization and robot lifespan. During commissioning and then during production, the goal is to continuously monitor the data to be able to send an alert when Scope detects that something is going wrong. So, despite not using AI, but again, human knowledge and predefined sets of rules to send and generate this alert, we provide a really easy to understand result with a color code. So green, everything is okay. And when you start seeing orange and red colors, that means the robot is deviating and we have a deviation in the production process. And the whole objective now is to be able to detect the pattern, the deviation pattern. And for that, we have, of course, a couple of examples that we identified at customer site. The first one is when you have this abrupt change in the results. So everything goes normal and all of a sudden there's a spike in the motor current, something is going wrong. This is usually the case when there's a point teaching and the point of the robot is badly taught, creating a constraint. So the robot is exerting a constraint against its environment. So this is really hard to see with your own eyes, which is also why it's interesting to have data getting analyzed. We have all sorts of sporadic issues. So this is mostly when you have a problem related to a specific trajectory, which is executed from time to time by the robot. And we also have slowly and degrading results. And this is usually a pattern that we have when there's a mechanical part of the robot that is end of life. So in that case, we were able to detect approximately 10 days before the robot was failing, that an issue started to appear in the data. So one challenge we faced with this first step, so this detection phase of predictive maintenance, is being able to detect is one thing, but now you need to warn the end user and send a message to the end user that something is going wrong. So in most of the IoT solution we see today, there's a notification on the dashboard, so it's usually a web-based interface, but the customer is not checking that dashboard really often, so you need to push that notification and telling him that something is going wrong. And for that, on the scope, we have a Node-RED server, so this is the way we make the interface with existing software solution at a customer site. So by supporting MQTT, HTTP, and WebSocket protocols, so if you cover those 3 protocols, you cover most of the cases. We are able to interact and communicate with the APIs of solutions installed at customer site. So this is really a learning we take from this challenge, is if you build an IoT solution, please, we suggest to make it open to be able to be well integrated in your end customer software ecosystem. So now going into step 2, so this is doing the same thing with AI. This is where things also get really interesting. And the first challenge we face working with AI is, of course, how to collect data. Because when you talk about AI, you train machine learning models and you need a lot of data. And so getting that data from the customers is not always very easy. And there's 3 ways you can do this, and 3 different architectures. The first one is to have a product which is running on the production line and doing the computation directly on the production line. So that means you equip your customer with a quite a powerful hardware, because it has a lot of storage to store the history of all the data and a lot of computing power to run your algorithms. So of course this has pros and cons in terms of cybersecurity and IT acceptance. This is very well accepted because you have no internet connection between the production line and the cloud. But to get the data from that is quite expensive, because you need to have someone that goes on the production line to actually extract the data. So the data collection is expensive and not automatic. So this is why we also have 2 other types of architecture to get the data. So a cloud connection, so as long as the customer accepts that his production line is connected to the cloud, you mainly have 2 different types of architecture. Either you send the message from the robot to the cloud going through the internal network of your customer. So in terms of integration, this is a bit harder, because you need the IT guys, you need the maintenance guys to be well aligned to let the message go through the whole architecture. But this is, in terms of cybersecurity, more accepted. And then you can also have a network that consists of bypassing the internal network of the customer by equipping this small device with a SIM card, so directly connect the production line to the mobile network. So again, in terms of pros and cons, the integration is really plug and play, but we rarely see customers willing to do that on the production line. So the learning we get from that, getting the data, is a challenge for every robot manufacturer, I guess. And so we decided to have a flexible solution to adapt to customers' needs and IT regulations at customer side. So generally speaking, we see big customers with big IT team and IT regulation. They prefer to have everything running on premise. And smaller enterprise may be more flexible, allowing us to also connect their production line to the Stäubli cloud. Another challenge we get from stepping into AI is how we will be able to build the perfect theoretical model. So to be able to detect that something is going wrong on a robot, you also need to know exactly how a perfect, healthy robot in a perfect world should behave like. And so this difference between your actual measurement and the theoretical model will help you identify that an abnormal behavior or defect is currently happening. So what we call, to put it simple, what we call a theoretical model is my robot is going from point A to point B, and this trajectory is characterized by the sensor signal. So my theoretical model will try to predict what my sensor signal will look like from A to B, and this includes the motor current, the position of each joint, and of course the duration it will take for this robot to go from point A to B. So now, to be able to build this model, we need to know and understand what has an impact, what will have an impact on on this sensor data. So with a traditional and very simple model, and this is what we have been done in the past, of course, the location of A, the location of B will have an impact on the data. The speed of the robot model, so if it's a big robot or a small robot, and of course the payload, so if the robot is carrying a heavy payload, this will have an impact also on the model. So this is traditionally what we have done in the past, and using AI, we have been able to take into consideration even more parameters to feed in this theoretical model. For example, this is a few examples, the oil temperature. So the colder the oil inside of the axis, the more viscous it will be, so the more current you will need in the motors to move the robot from A to B. So this is an example, and using machine learning, we are able to take in a lot more parameters inside of this theoretical model, and to really close the gap between the reality and the theory. So the learnings from that, AI is usually mentioned to detect wrong behavior, but can also be used to determine what a good behavior is. And this is what we do at Stäubli. And remember the slide when I talked about why we decided to focus on predictive maintenance. We believe that robot manufacturers have the most comprehensive knowledge about how the robot is built and how the robot should behave. So they're the best candidate actually to build this theoretical model. So now we have been able to detect an issue using AI. It's time to understand and identify the root cause of the issue using classification. So here, during the step 2, we had a data collection challenge. So this gets even more complicated because it's easy to get data from a healthy robot. It's a lot harder to get data from a robot that is failing. And as a rule of thumb, you need between 10 and 100 occurrences, so 100 data sets per defect that you would like to identify to be able to train a robust machine learning model. And of course, this is made very complicated because first, Stäubli robots never break, so it's hard to get this data. And the second reason is that usually robots are following a maintenance plan, so we change parts on the robots at fixed time interval before they actually break. So it's hard for us to get faulty robot data. So a learning from that is at Stäubli we have a big facility, what we call the endurance testing facility, where we have robots running around 24/7 until they break. So we equipped every robot with, of course, a scope box to be able to have this faulty robot data acquisition. And so a learning that we have to speed up this process is that even if you do not have an AI project ongoing, it's a good practice to start collecting data even before you identify what you want to work on. And now we have cats. So another way to speed up the acquisition process is to use a data augmentation technique. So this is a technique that is widely used for image recognition. Is that by using one occurrence of image and tweaking the image a bit around, you can expand the data set and thus speed up the data acquisition. And so then, when you have detected the issue, classified the issue, this is time to go to prediction. So this is a bit of the uncharted territory for us. We're still working on step 3. And we made a lot of progress over the years, even if the hype has been slightly going down. And we're starting to get a lot of positive results from those first 3 steps. And we do believe, as a conclusion, when you see the growth of AI in the coming years, that this will accelerate a lot. So I hope that during the next presentation I will give, we will be able also to present our predictive maintenance algorithm. Thank you.
So you've set up the questions here for yourself because you just said your robots never break. So anyone wants to challenge that?
It's true. It's true.
No, do we have any questions for Clément at all? Again, just raise your hand. And yes, over here. Bertus, I think.
Hi, great presentation. Thanks for that. I was wondering, you have this scope box. You said it has a lot of computing power. And is such a thing needed for every single robot?
So we can connect up to 50 robots to the same box.
Ah, okay.
Yeah. So to give you an idea, we can store approximately 1 year of history if you send a lot of data and you connect up to 50 robots. So you can connect 50 robots to the same box.
Yeah, so the power consumption of that PC or that device is in effect very little to...
Compared to the robots, of course. Yeah.
Okay. Thank you.
Okay. Anyone else? Yes, right at the back there.
Thank you for the presentation. Actually, we met the same problem when we trying to predict maintenance. We have quite limited negative samples to train the AI, and then we trying to find more data during the process of R&D of new product. Do you have any experience about combine these two together to develop this AI-based knowledge and during the stability test?
So experience in collecting and training the models?
Yeah.
Yeah, so there's 2 ways we're looking into training models, of course, offline, so getting the data, as I explained, and then training the model. And I think someone also mentioned earlier today that using neural network directly in the controller, so in the robot controller. So at Stäubli, we've made some experimentation. We have a PCIe Express port, and we connected an NPU board to be able also to run neural network directly on the controller. So there's two ways you can do this in training the models and running the models on the controller.
Okay, thank you.
Hope that answers the question.
Yeah.
Okay. And yeah, I think because of time, we might, if it's okay, if Clément is still here after his presentation, I'm here with connecting the 2 of you.
Yeah, and with a cold beer at the dinner, we can discuss
Perfect.
that.
Okay, thank you very much. And thank you for those insights in predictive maintenance. Clément Fournier, everyone. Thank you.